Okay, so consider the differential equation here. Find y equals g of x, the particular solution to the given differential equation with initial condition g of 0 equals 5. Okay, so the first thing that you have to do is separate the variables. So I want the y's over here and the x's over there. So I go like this, dy equals dx. Okay. And then you take the antiderivatives of both sides, and you have to make sure your notation is good. So we go like that. And then over here, this, if you let this be f, then f prime is the numerator, because the derivative of y is 1. I know you might be thinking 1y prime, but over on this side, y is the input variable. So, you know, if I were to think about the derivative of y when I'm on this side, it is just 1. So then, so we end up with, so anytime you have the integral of f prime over f, here's the formula. It's the natural log of the absolute value of f. So if I use that formula, I get the natural log of the absolute value of f is y minus 2. Equals, now this side, 1/3 x to the third plus x plus c. So let's see what I would have gotten so far. So I'd get 1 for separating the variables. I'd get 2 for the antiderivatives. And you can all do that. Okay, so then I've got to get c. So I use the initial condition, g of 0 equals 5. So this is x, that's y. And then we get the natural log of the absolute value of 3, because I plug 5 in, equals, and then 0 goes in here, so we just get c. All right, so what we have is that c is equal to natural log of 3. Notice I dropped the absolute values because 3 is already positive. So the absolute value of 3 is the same as just regular 3. Okay, so then we've got natural log of y minus 2 equals 1/3 x to the third plus x plus the natural log of 3. And then you put a base of e on both sides. And e and natural log cancel out. So this is just y minus, it's just that, equals e to the 1/3 x to the third plus x times e to the c. Now this c is not the same as this c. Okay, c just stands for any constant. Okay, c stands for any constant. Okay, but we can actually find the specific constant if we use this. Wait. Oh, no, what am I doing? I found it. Sorry, I got distracted. Natural log of 3. Yeah, duh. Okay, because natural log of 3 is where the c was. All right, so then, and these cancel, so that's just 3. So we have this equals 3e to the 1/3 x to the third plus x. Now we want to solve for y because they asked us to find that. Okay, it's a function. So we got to solve for y. So I want to drop the absolute values, but in order to do that, I have to go plus or minus. Dropping absolute values is the same as like when you take a square root. You have to account for positive and negative. Okay, but then you have to, it can't be both of them. So you have to ask yourself, do I have any information before this that tells me whether I want the positive or negative value of this? And you always look at the initial condition. Here, the output is positive, okay? So we are going to want the positive one, or the one that would make y positive. So imagine adding 2 to both sides. You know, it'd be, we want a positive number plus 2, and that would still give us a positive number. So it's going to be the positive one. So x equals 3e to the 1/3 x to the third plus x plus 2. So you add 2 to both sides. And that is it. So see where else we got points. Solves for y. for getting the constant of integration and then this. So that was 5 points right there. And guys, you really can do that, okay? And I'm speaking to every one of you. You could definitely get points on that. All right, now this next one. For the particular solution that we found in part A, find this. Now, if you didn't get this right, this is hopeless, this one. But, so, you try anyway. And this is 3e to the 1/3 x to the 3rd plus x plus 2, okay? All right, and now you're plugging in negative infinity. So you think of like -10, -100, -1,000, -10,000, like -1,000,000, -1,billion. So you're plugging in all of these negative numbers in here. Well, guys, a negative to the 3rd, so if you plug a really big negative in here, it gets cubed. So you end up with a really big negative. So you've got a really big negative plus a really big negative. This is a huge negative that just keeps getting bigger and bigger and bigger and bigger. So you end up with 3e to the negative infinity plus 2. All right? But what happens if we make this positive? This is 3 over 1. Or let me leave the 3. Sorry, you don't have to erase that, but it's just a little more sophisticated to just go 3 over e to the infinity plus 2. So if you've got 3 over an enormous number, okay, or 3 over e to an enormous number, 10, 100, 1,000, 10,000, etc. This is getting huge. 3 over a huge number is a very small number that just keeps getting smaller. So this is 0 plus 2. So that's 2. And that is just 1 point there. Okay. And now, this last part. So let this be the particular solution to the given differential equation with initial condition this. Initial conditions are very important. Okay, they're going to help us get the constant of integration, so they're going to help us find c, and then they're also going to help us at the end to choose between a positive or a negative, which doesn't always happen, but it does often. So find the value of this. So this is the second derivative of y with respect to x. If you read it literally, it's like d squared y over dx squared. You could read it like that literally, but what it means is the second derivative of y with respect to x. And then you could say y double prime. But this notation doesn't make explicit what the input variable is. That's why sometimes Leibniz is more beneficial, especially when you have to do implicit differentiation. You should know, they should use Leibniz to tell you what's the input variable. So anyway, is the graph of this, okay, so we're going to find the value of this, the second derivative at this point. And then we're going to say, answer, is the graph of this concave up or concave down at that point? And then we're going to give a reason for our answer. Okay, so we got to go back to the beginning. Guys, so often, these AP problems, you just go back to the beginning to do, to tie things together. So they told us that this was y minus 2. Okay. And now I need the second derivative of it. So this equals, okay, so I've got to use product rule. So guys, I know that you're kind of past this, but I have noticed sometimes people are having trouble with product rule, so I'm just going to do the brackets, even though I think oftentimes you don't feel the need. Okay, so I put the original functions in there. And now I take their derivatives. So, yeah, the derivative of this is just 1, and then you do y prime, because it's dy dx. And then I'm just bringing this down, plus that I just bring down. And then the derivative of this is 2x dx dx. So it's just 2x because the dx over dx is a 1. Okay, and then in for this y prime, I'm going to put this, okay? dy dx and y prime are the same thing in this situation. So I'm getting that this is equal to y minus 2. Okay, so this is y prime. Plus, okay? And then, guys, I noticed that I could factor out y plus 2. Okay, so from those two things, we can factor a y minus 2. Okay, and then left inside is this times that. So x squared plus 1 squared plus just 2x. Okay. All right, so there is that. And let me see what they give us for that. No, we don't get anything for that. We get something for plugging the point in and getting the number. Okay. So the way you use the notation to do this is like this. Okay, so the second derivative of y with respect to x evaluated at 1, 3. Okay, and that's equal to, okay, so 3 goes in there, and I get a 1. 1 goes in here, and we get 2 squared plus 2. So this is equal to 6. Okay, so we get 2 points for that. Okay, and there's only one more point to get. We've got to tell them if the graph of y equals f of x is concave up or concave down at this point. Okay, so the graph is concave down at 1, 3, and then you have to say why. This is a Susan's table situation, okay? If you hear increasing, decreasing, relative max, relative min, inflection points, concave up, concave down, all of that is Susan's table. Okay, so, yeah, you've got to look at Susan's table, or you won't be able to on the test. You've got to know it. When is a function concave down? When its second derivative is positive, okay? Okay, so we're going to say because the second derivative of y with respect to x evaluated at 1, 3 is greater than 0. That's all, okay? You have to tell them, and guys, a lot of you, no, probably not a lot of you, but a lot of students, and I learned this at an AP seminar, they like to say because it is something. They're not going to give you any credit if you describe something, if you in an explanation say because it is concave, or because it is greater than 0, because it is concave up. If you are thinking about Susan's table and you use it to describe what you're talking about, they're not going to give you credit. Okay, so make sure I'm telling them that the second derivative at that point is greater than 0. I didn't say because it is greater than 0. Yeah, that's like a lot of people do that all around the country. It is normal. All right, guys, I'll talk to you later.